successful in the description of some phenomena, and in particular it is very successful in combination with LDA or GW for the description of real materials. In particular because it is able to capture the MOT, metal to insulator transition, and because it is very efficient in the description of local observables, because the description of local quantities at the single particle level is exact. But we have some drawbacks in the DMFT method, because first of all, the self-energy is momentum independent. So any phenomenon which is related to the momentum dependence of the self-energy is neglected. And additionally, collective excitations are not fully described inside DMFT, because collective excitations usually have a very strong non-local behavior. Additionally, we know that DMFT is exact for infinite coordination number, so infinite dimensions. But if we want to study two-dimensional materials like cuprates or transition metal dechalcogenides, two dimensions, infinite dimension is not a good approximation. And for this reason, we have to develop some tools that go beyond DMFT, but at the same time is able to keep all the positive advantages of DMFT. So let's start from the model I will be using during this talk. And the model is the extended Hubbard model. The action of the model has three terms. One is the single particle term that contains the dispersion. The second term is the local Hubbard interaction. And the third term is the non-local Coulomb repulsion, which has a channel index that can be either charge or spin degrees of freedom. This model is specifically interesting because it contains all the physics of the Hubbard model, and additionally includes the possibility of addressing an important phenomenon which occurs in real materials, which is the charge density wave phase, which of course depends on this non-local interaction, and hence is not included in the Hubbard model. There are many ways to try to address this problem of the extended Hubbard model. So we can follow calculations from cluster DMFT, or apply methods like d gamma A, or even some exact method like connected determinant diagrammatic Monte Carlo. But in this talk, I will focus on what we can do starting from the DMFT framework, let's say, and extending this framework using what are known as dual transformations. Dual transformations are based on the concept of splitting this action into a part which is an impurity, which at this point is arbitrary, plus some non-local part which depends on the dispersion and on V of Q, so on the non-local quantities. And at this point, we can perform an Hubbard-Stratonovich transformation, which involves only the non-local part. And this allows us to describe the system in terms of new variables, which are based on the impurity and perturbative in this non-local part. So in order to be more specific, I will use the dual boson transformation that maps the electrons into dual fermions and dual bosons. And dual fermions describes something which is close to the non-local part of the Green's function of the electrons. And the dual bosons are described by this bosonic propagator, the wiggly line, which is proportional to some RPA version of V of Q, which is stressed by impurity quantities. Additionally, we have that these particles interact with each other, and the interaction takes two different forms. One is a 4 fermion vertex, so 4 fermion interactions. Here the white dot means incoming particle, and the black dot is outgoing particle. And a fermion boson vertex, where here we have a connected boson to this slot. At this point, in order to rewrite this theory in a way which can be efficiently used in the framework of diagrammatic Monte Carlo, we can integrate out the bosons, and we introduce an effective 4 fermion interaction, which contains the 4 fermion vertex and some additional interaction, which is mediated by a boson exchange. And we decided to start from the single side impurity, DMFT impurity solution. So this wiggly line depends on V only, or depends on V. It's roughly proportional to this RPA V. And when we go, so we performed a dual transformation, and we included bosonic variables, and then we integrated them out. So it might look that we go back to the initial point, but this is not the case, because in performing this transformation, we have the possibility to dress this wiggly line with local quantities. So we actually gain something, because the bosonic propagator contains more than just the bare V of Q. And to go back to the connection with non-equilibrium problems, this is the calculation of these vertices is actually the main difficulty for the implementation of dual boson to non-equilibrium problems. So now we have a theory that contains effective fermion-fermion interactions, and a line that describes the propagation of particles. And we can start to construct the Feynman diagrams that describe the processes order by order. So for example, for the self-energy, we have the sum of all these connected one particle irreducible Feynman diagrams with 2 external legs. The problem is that we will soon realize that the number of diagrams at any order increases as n factorial. So it is impossible to sum them one by one. And we have to come up with some efficient method to sum these diagrams, like numerically. So there are different ways. One can use some approximated methods based on resummation of diagrams, as for example, ladder dual bosons. But these methods are topology selective, so they choose just some specific kind of topologies. On the other hand, we can proceed using this expansion order by order, and we can truncate this expansion at some maximum order and max, and we realize that we can rewrite any observables in terms of a sum over all the orders, a sum over all the possible topologies, and internal degrees of freedom, which appears due to loops in the diagrams, multiplied by the sign of the value of the diagram, multiplied by the absolute value of the diagram. We do this because then we can use this diagrammatic Monte Carlo method in order to perform a perturbation theory at arbitrary order. And the splitting into these two parts is important because once we realize that this absolute value can be treated as a generalized probability, we can apply Metropolis-Hastings algorithm to sample the sign of the diagram with respect to this probability distribution. This method is unbiased, and meaning that it's not topology dependent, and it allows direct evaluation of observables. In order to perform efficiently this Metropolis-Hastings scheme for the generation of diagrams, we can use a worm algorithm, which was developed by Nikolai Prokofiev, and in this context of DiagMC, and it is based on the creation of some unphysical propagator that allows for the creation of different topologies. So if we start with a vertex which has a line connected to it and also other lines, but we will focus on this one only, we can create this worm which carries some momentum, and we can start to move the extremal point of this worm around. And at this point, these kind of diagrams will be unphysical because they have this non-physical propagator. The point of doing this is that after some Monte Carlo steps, we would get to some configuration like the one shown here below. And in this configuration, we can simply split the upper and the lower propagator, delete the worm, and insert a vertex. So this means that we moved from order n to n+1. And additionally, the converse move is allowed and allows us to go from order n+1 to order n. So these Monte Carlo updates are all obtained by this acceptance probability, which gives the probability of a given configuration multiplied by the absolute value of the diagrams divided by the initial quantities. So we came up with a novel computational scheme, which is based on dual boson transformation. So we start from strongly interacted electrons and we go to, well, supposedly more weakly interacting dual fermions and bosons. And we can exploit this to construct perturbation theory at arbitrary order using diagrammatic Monte Carlo. This method works for arbitrarily strong U. It can include non-local V of Q, and it is able to sum all the diagram topologies up to a given order. The drawback is that we implemented this for a single site impurity problem. So if we want to go to lower temperature and we want to address phases like the antiferromagnetic phase, we need to do something a bit smarter than that. But let's go to the analysis of the result. So here on the right, you can see what the output of the calculation is. So what we actually get from a calculation is the dual self-energy. And the dual self-energy is exactly related by a simple equation to the real part of the self-energy. So we can then analyze our output order by order, and we can see if the results are converged up to a given order, or if we have to do something better. So this method, as you can see, allows for an improvement order by order. So it's a controlled method when it converges. Now here we can see that for the real part of the dual self-energy, order 2 is already probably enough to describe most of the physics of the system, because order 2 is very close to the higher orders. But if we now then look at the imaginary part of the dual self-energy, we see that second order is quite off from highest orders, and order 3 is already able to capture most of the physics, but it's still missing some contributions. So we can say that order 2 is usually enough to describe the real part, and order 3 would be enough to describe imaginary part. In order to be sure, we always go up to order n equal 5, and this is enough to describe the system away from instabilities. If we get close to instabilities, then we need highest order of perturbation theory. Below here, I show the electronic self-energy varying the value of V. So in this case, it's nearest neighbor Coulomb interaction. So it's described by just one parameter V. And you can see that the real part of the self-energy is grows linearly in V. So these lines are equidistant to each other, while the imaginary part of the self-energy behaves in a non-trivial way on V, because it depends on higher order diagrams. So we additionally performed some comparisons with ladder dual bosons. So these comparisons had two aims. One was to first of all, to check the implementation of our method, and the second was to benchmark the results from ladder dual boson against the DiagMC results. So if we look at these plots, so here I show different lattice self-energies at U corresponding to 1/4 of the bandwidth, a half of the bandwidth, 3/4 of the bandwidth, and the bandwidth. And here you can see that up to half of the bandwidth, the results from ladder dual boson and diagrammatic Monte Carlo match quite well. I mean, they match very well because they are equal to each other inside the Monte Carlo noise. But as soon as we go above the bandwidth, or more precisely in correspondence with U equals 6, we see that there is some mismatch between ladder dual boson and diagrammatic Monte Carlo. And if we go to U equal 8, we can observe the same phenomenon. But at the same time, we see that in the real part of the self-energy, this behavior, like the mismatch becomes smaller as V increases. Concerning the real part of the self-energy. For the imaginary part of the self-energy, the mismatch remains there. It might be a bit less severe at large V of Q for U equal 8. We developed an explanation for all these phenomena in order to describe all the mismatches and the convergence properties of the series. The nice thing about the diagrammatic Monte Carlo is that it allows to go order by order. So it is possible to address the various contributions that arise from each order. So if we start from the ladder diagrams, we know that ladder diagrams are diagrams of this kind. We have some purely fermionic contribution, and then we have some parts where the main contribution is an horizontal bosonic excitation. Of course, there are more diagrams here because this line in the ladder approximation are usually renormalized. But the main point is that in comparison with our diagrammatic Monte Carlo, some diagrams are missing. So if we start an order by order analysis, we can see that at the first order, the self-energy in dual boson diagrammatic Monte Carlo corresponds to this kind of diagram. This kind of diagram contains an orange box connected by a Green's function above, plus this dual boson diagram. But due to the DMFT self-consistency condition, the first diagram vanishes, and we are left with this contribution only. Additionally, if we go to second order, we have diagrams of this kind, where we have two violet boxes connected to each other. And we checked that the main contribution to these diagrams comes far away from phase transitions and instabilities, comes from this dual fermion diagram. So second order dual fermion diagram. The reason why the real part of the self-energy coincides in most of the regime with ladder approximation is that these two diagrams carry the main contribution when the interaction is relatively small, so below half of the bandwidth, and additionally, if we want to describe the imaginary part of the self-energy, we need to include more contributions to these diagrams, because we need to go up to third order. This is the reason why the imaginary part of the self-energy is much more sensitive to mismatches between the two methods. We also plotted the values of the mismatch between the two methods at different values of U. And we realized that the biggest difference occurs around the Mott phase transition. So when U is between 6 and 7, let's say. And this is a very interesting regime because it's the only regime where diagrams like that have only horizontal excitations or are described by perturbation theory are not the only important contributions to the self-energy, but we can have other diagrams that contribute to that, like this multiple fermion scattering, or this mediated by bosons, or this mixed bosonic and 4 fermion interactions which are mixed to each other. And these diagrams are not included in ladder dual boson. The next thing that we studied using our method is the charge density wave instability, which is one of the most interesting phenomena emerging in the extended Hubbard model compared to the Hubbard model. So it consists in a phase where we have a chessboard configuration where doubly occupied sides alternate with empty sides. And this configuration is an insulating configurations because if I move one electron from this side to this side, it will experience the interaction with all the neighboring sides, which corresponds to V. So if V is large enough, this hopping to a neighboring side will be extremely disadvantageous from the energetic point of view. So this is why for this, for a square lattice, perturbation theory predicted a value for this transition around U divided by 4. And we also we see that since this phase is insulating, we expect the emergence of some pseudo-gap physics in single particle observables. What we did then is to plot the spectral function at the Fermi surface in the UV plane. And indeed, we observed that at some point of the, for some values of V, we see some decrease in the spectral function. And after this decrease, we immediately see some divergence of the spectral function. So here the blue color means that actually the spectral function didn't properly converge. But if we check the values where this happens, they are quite off from this relation. And this relation was shown to be quite consistent with DCA calculations, which in these situations are basically exact calculations for these temperatures. So,
Matteo, sorry, you have 10 more minutes to go, including discussions.
Okay, thanks. What can we do to overcome this problem? We can do something better since we are using diagrammatic Monte Carlo. And what we did was to plot the value of this spectral function order by order. And since at finite order, all these functions are basically like some analytical function of V because they are based on polynomial expansion, we can plot them and we can see that they have some kind of Fermi function behavior, let's say. So they're non-zero and they drop to 0 in correspondence of some value. Interestingly enough, this value decreases as the order increases. So we expect that if we increase the order even more, so here it's plotted up to order 6, we expect that for order 7 and order 8, the position of the transition will be even shifted to smaller values of V. So what we did was to interpolate each one of these curves And for each of these curves, we get the middle point of the Fermi distribution. And now, if we plot the middle point of this Fermi function as a function of the order n, we see that it actually decreases, and it really looks like it converges to some value. So we interpolated this curve, and we obtained the extrapolation at infinite order. And then we performed some calculations using ladder dual boson and plotting the inverse susceptibility at the end point. And it turns out that the values obtained by diagrammatic Monte Carlo and ladder coincide very nicely. So we may ask ourselves if this is like just coincidence that the convergence is really so good. But then we did the same for u equal 3.5, and we found the same behavior. So this method looks quite solid to find the actual position of the charge density wave instability using single particle quantities only. So here's the summary. We did a dual boson transformation that already accounts for local correlations, and hence it contains all the good, the advantages of the DMFT, but it allows for an exact diagrammatic expansions around the DMFT. Then we integrated out the bosons in order to obtain an effective non-local vertex, which is suitable to perform diagrammatic Monte Carlo calculations. Finally, we realized that using an order-by-order analysis, we can obtain observables in the infinite order limit, and we can also understand which are the more important contributions in each regime. We applied this method to the charge density wave phase transitions, and we also compared the results with ladder calculations, and we realized that the biggest mismatch between the two methods occur around the MOT phase transition, and there is a precise and reason for that I described before. So the new perspectives are the analysis, like the implementation of the susceptibility, or other two-particle observables, like beta salpeter kernel, for example, is a candidate. And we can add some breaking symmetry term so that we can either include charge density wave phase or antiferromagnetic phase. That would be very interesting. We are currently benchmarking the Trilix square approach using diagrammatic Monte Carlo dual boson, and the results are very promising. And finally, we also hope to extend the applicability to lower temperature, maybe using a skeleton expansion or some different impurity problem as starting point. And finally, it would be very interesting to include more than one band. This is extremely complicated because the program doesn't scale very well with the number of bands, but we hope that, for example, tight binding on honeycomb materials with two bands are doable. So thank you for your attention, and I'll be glad to answer your questions if you have any.